In this work, we propose techniques for tracking the micromotion of multiple objects outside the line of sight using only commonly available imaging components. In this illustration, two objects move along small, intricate trajectories. Both objects are occluded by a sidewall. Neither the camera nor the light source are in direct line of sight of the objects. We show that, under certain assumptions, the problem of tracking objects around the corner is analogous to tracking objects with a direct diffuse source and a direct bare sensor, as shown on the right. Given this analogy, we first show tracking results for multiple objects in direct line of sight with a bare sensor to evaluate the capabilities of our multi-object tracking approach without the added complexities of non-line of sight tracking. An interesting test case is tracking the hands of a wristwatch. For experimental purposes, the watch face was painted black, and the hands were painted white. As shown on the right, the watch face is illuminated by a diffuse laser and imaged by a bare sensor. The input to our algorithm is the bare sensor image shown on the right. The high-frequency noise-like speckle pattern is due to coherent light from the diffuse laser source interacting with the optically rough surfaces in the scene. Our goal is to track all three hands simultaneously, using only the speckle images. This is a challenging problem because the speckle images do not provide any spatial specificity, and the constituent motions in the speckle sequence due to different objects are superimposed over the entire image. Here, in the lower left, we see the tracking result for the second hand, expressed as a rotation angle over time. The second hand movement is clearly visible, even in the conventional camera, and so it's perhaps not surprising that our measured results closely match the ideal of 6 degrees per second. However, it's much more surprising that our approach can simultaneously track not only the minute hand, but the hour hand as well, which moves 720 times slower than the second hand. Despite this large dynamic range in motion, our approach accurately recovers the trajectories of all three hands. We now show results for tracking objects around the corner. For these experiments, we built an enclosure to act as a small room. A camera with a macro lens images a small patch on the far wall of the enclosure, and we use a high-precision translation stage to move the target object. A collimated laser illuminates a spot on the far wall, which acts as a virtual diffuse light source. A top view of the enclosure is shown at the bottom. The walls are covered in black material to improve the signal-to-noise ratio. The target object is a 25 mm diameter chalk disc. The laser illuminates a spot on the left side of the wall, and the camera records the patch on the right. In this first experiment, the object moves in a small spiral trajectory. The object motion is exaggerated here for illustration purposes. As the object moves, this is what the camera records. If you look closely, you may be able to see a faint moving speckle pattern. It's possible to isolate the moving speckle pattern. First, we compute the mean image of the sequence, shown here. Then, by dividing the raw captured image at each frame by the mean image and normalizing, we recover the ratio image sequence. The moving speckle pattern is now more clearly visible, and we can use it to track an object around the corner. This shows the tracking result with respect to the amount of shift of the speckle pattern over time. Given speckle shifts, it's possible to recover the motion of the object, given the linear relationship between the two. Here, speckle motion has been mapped to object motion, and we see that the estimated results are very close to ground truth. Using our technique, it's possible to recover small, intricate object trajectories with high precision. We now move to the much more challenging case of tracking multiple simultaneously moving objects around the corner. In this case, two objects move along spiral trajectories. Again, the motion is exaggerated here for illustration purposes. Even after the ratio images are computed, the motion of the speckle pattern is much more chaotic than the single object case. We propose a novel clustering algorithm that not only computes the constituent speckle shifts in the ratio image sequence, but labels them over time to enable tracking. Here we see tracking results for two objects. Recovering the motion trajectories of 3 objects is also possible, as shown here. In summary, we showed that tracking objects outside the line of sight is analogous to tracking objects with a direct diffuse laser source and a direct bare sensor. We developed novel techniques that exploit the unique properties of speckle images to enable the recovery of the microtrajectories of multiple, simultaneously moving objects using this analogous setup. Finally, we showed for the first time that it's possible to track the intricate trajectories of single or multiple objects around the corner with high precision using only commonly available imaging components. For more details, please see our main paper and supplementary technical report.